Hi and welcome. In this video, I'm going to provide you with an introduction to random forests for regression. Now, prior to watching this video, it's a good idea to first watch the video Introduction to Cart Decision Trees, because cart decision trees form the foundation of the random forest algorithm. Now, the main idea of random forests is to fit multiple cart trees to independent, what we call, quote, bootstrap samples of the data, and then combine their predictions. Now, random forests can be used for either classification or regression, and Leo Breiman, who was one of the co-creators of cart decision trees, also created random forests, and he published a paper on this method in 2001, and Leo's pictured here. Now, our random forest software was actually developed in close consultation with Breiman himself. So before we go into the random forest algorithm in detail, let's first discuss bootstrap sampling. Now, a bootstrap sample is a random sample conducted with replacement. So the steps to construct a bootstrap sample are the following. So you randomly select an observation from the original data. So let's say that this is our original data. So take an observation. Then what you do is you write this observation down. And by this I just mean record it in some way. So write it down. And then what we do is we just put it back. So take this and kind of put it back in the original data. And when I mean put it back, what I mean is you can take the same observation more than once. And so what we do is we just repeat these steps n times, where n is just the number of observations in the original sample. So take an observation, write it down, put it back, take another one, write it down, and then before I put this back, notice that the same observation was selected more than once, and that can certainly happen. Again, that's because we're sampling with replacement. So take this, and then we put it back, take another one, write it down, this one has missing values, put it back, and then keep doing this until you have n observations. And so your final result here will just be one bootstrap sample with n observations, which is what we see here. Okay, so that brings us to the random forest algorithm for regression. So here what we do is we draw a bootstrap sample from the original data, and then we fit a large unpruned cart tree to this bootstrap sample. The twist here is that at each split in the tree, consider only k randomly selected variables instead of all of them. So we build our tree, and then what we do is we just repeat steps 1 through 2 b times. So here's another one, and then here's another tree, and keep going. So here's another bootstrap sample, build another tree. Notice how all of these trees are different. And then finally, at our bth bootstrap sample, build another tree. Okay, so this collection of trees that you see here, this is actually the random forest itself. So a random forest is nothing more than just this collection of cart trees that you see here. Now, to predict a new record, what you do is you run the record down each tree each time computing a prediction. So maybe you take a record, you run it down the first tree, and you get 10.5. Maybe you take the record again, run it down the second tree, and you get 9.8, and you keep doing that. Now, to predict a new record, what you do is you just take the average of these b individual predictions. And so the third step here is just to average the predictions to predict a new record. And this is your final prediction. And then of course you can repeat this process for all records in like a test data set. But we'll talk about that a little later. Okay, so when you're building random forest models, just kind of keep this picture in the back of your mind. So here, remember, we're just taking the predictions from each of these cart trees and we're just averaging them, and there are b of them. Now, the reason we use random forests is because they generally have superior predictive performance versus cart trees. And this is because random forests have a lower prediction variance than a single cart tree. Now, since random forests are a combination of cart trees, they inherit many of cart's desirable properties. So one is the variable selection, the interaction detection, nonlinear relationship detection, missing value handling, outlier handling, the modeling of local effects, and they're not affected by monotone transformations of predictors. However, the one drawback of random forests, as you can imagine, is that it's not as interpretable as a single cart tree, and that's because we now have hundreds of these trees, or maybe even thousands. Okay, now the performance of a random forest model is actually dependent upon the values of certain model parameters. And two of these parameters are the number of trees and the number of variables chosen in each split. So really, in the context of our algorithm here, we're looking at B for the number of trees and K for the number of variables chosen at each split randomly. So the default value for the number of trees is 200, and really what you want to do is you just want to make the number of trees large enough so that the model error no longer meaningfully declines as the number of trees increases. And so to do this, you're just going to have to experiment with different values. There really is no rule of thumb. It's always going to be dependent upon the data set. Now, one thing to just be aware of is that in random forest, the optimal number of trees tends to be the maximum value allotted, and this is due to the law of large numbers. This is more of a theoretical property of the random forest. We don't really have time to get into that today. So, to give you an example here, what I mean by choosing the number of trees is, if we look at this curve here as a function of the number of our trees, you'll see that there's really not much of a difference between the error for a random forest with 200 trees, which is here, and this is the default setting, and one with 400 trees. So at least for this data set, a larger number of trees will not improve the model meaningfully. And really, it looks like you could probably even stop at 100 or maybe even 50, and it kind of starts to creep up after before that. But so this is just going to be something that you'll have to experiment with in practice. Okay. So the second parameter is the random number of variables chosen in each split, and this is just K. So the default here is actually 3, and you're going to have to experiment with different values, and because the optimal value for K will always be dependent upon the data set. Now, a very efficient way to do this, and this is actually what I'm going to show you in the next video, is something called automate RFN preds. And so what this does is this automatically builds multiple random forests. But each time the forest is the same, except that the number of randomly selected variables at each split in each cart tree changes. So you're just going to change the value for K each time. And the reason we do this is because this allows you to conveniently determine the optimal number of variables to randomly select each split in each tree. And because if you think about what you'd have to do without this, you'd have to run the model once. Like for instance, here it's 3, you have to click start, and you would run the model. And then you'd have to maybe change this to 4, click start again, run the model. And then to 5, click start again, and so on. You could see how tedious that would be. So we put this nice automated procedure in for you. So the output from this procedure is going to look something like this. And what this output is telling you is that the optimal number of randomly selected variables at each split in each tree in the forest is just 5. And again, this is much nicer than having to just do this individually each time and then compare the error rates manually. Okay, so as I mentioned before, since a random forest is fundamentally a collection of hundreds or even thousands of cart trees, the simple interpretation is lost because we now have hundreds or thousands of trees and we're now averaging the predictions. So it's not like in cart where you have just a single tree. Now, one method used to interpret a random forest is variable importance. In a random forest, variable importance is calculated by summing the split improvement value for every split a variable generates in all of the trees in the forest. And we talked a little bit about this in the previous video on cart, about the split improvement, but really every time you split the data, you generate an improvement score. So you're just going to take that every time a variable is used and then just sum all of those up in the end. Now, one thing that you're going to see is the raw importance and also the relative importance. So in the top part, when we have this relative importance box unchecked, you can see the actual score itself. Now, what you do to get the relative importance is you just take the score divided by the largest score, and in this case, the score is actually the largest score. And then you multiply by 100, and then you get 100. And so that's where this number comes from. Now, for maybe x6 here, take the score, divided by the largest score in the forest here. And so in this case, that's just 4.34. Multiplied by 100, and then you get 15.2. And so that's where this value comes from. Okay, so now we're going to discuss how to evaluate a random forest using two methods. One is the test sample method, and the other is the OOB method. So for the test sample method, which we've actually already seen, but I just kind of want to formalize this a little more, let's say that we have data that we set aside, and we'll call this data the test data. And what we want to do is we want to compute error metrics for this test data set. So we'll just let R be a single record from this test data set with a target value of 9. Now what I mean by target value is the Y variable has a value of 9. And so what we would do is to predict a new record, that's the first step. So we run the record down each tree, each time computing a prediction. So you'll run our record R down each of these trees and you'll get a prediction each time. And so you have B predictions. And our final prediction for a new record is just to take the average of the B individual predictions. So our Y hat here, which denotes our prediction, is just given by this. Now, what we can do based on this is we can just compute things like the squared error. We have the 9, and of course we have the prediction here, so we can just plug this in and we'll have a value. And then what you can do is you can repeat this for all records in the test data set, and then use this to compute things like the test mean squared error. So our second method for evaluating random forests is the OOB method. So OOB stands for out of bag. Now out of bag data, this is just the records that are not selected in a bootstrap sample. And around 37% of records are not selected in a single bootstrap sample. Now the OOB data itself is actually used in a random forest to test the model. And the reason we use it is because, one, it's faster than cross-validation, and it tends to be more pessimistic than test data. Now, of course, you can still use the test sample if you'd like. Okay, so how do we compute this? Well, what we do is the following. So let R represent a single record with a target value of 9, just like we had for our test sample example. So what we do is we run R down all of the trees that did not use R in their construction. So key here is did not. So around 37% of the trees will be constructed without using the record R. So on average, a random forest composed of maybe 200 trees, like we see here, will have around 74 out-of-bag predictions for the record R. So maybe this tree was constructed without R, as was maybe this one, and maybe there was a whole bunch in the middle, and then maybe this one as well. Now what you do is you compute a prediction for each of the trees that did not use R in their construction. So run R down this one, this one, this one, and all the ones in the middle. So you'll have around something like 74 predictions if you have a random forest of 200 trees. And so maybe you'll have this first out-of-bag prediction, and then maybe this one, and then maybe this one. And then what you do is you just average the predictions made in step 1. And this is the record R's out-of-bag prediction, which is here. And then finally, you can compute the error using the prediction from step 2. And so this is R's out-of-bag error, and this is actually its squared error, if you want to be more precise. Now, the reason this is nice is because we can repeat steps 1 through 3 for all records, and you can also compute things like the out-of-bag mean squared error. And so this Y hat OOB, this is just the prediction here. I just use this for notational convenience. And so when you see things like this in the output, this OOB column, you at least have an idea of how the procedure works. Of course, for different metrics, the formula is going to change, but this is the idea of the procedure. Okay, so that concludes our basic introduction to the random forest algorithm. In the next video, we're going to go into the software and we'll build a random forest model. And we'll also run some simulations and show you how to optimize some of the parameter values. Now, if you have any questions, then please feel free to contact us at support@salford-systems.com, and I will see you in the next video.